Hello everyone. Today we're going to be talking about acids and bases and some of the math that we can do with that. So what can we know about acids and bases quantitatively? So say for example we add 1 gram of sodium hydroxide, NaOH, into some amount of water, right? What happens when we do that? So hopefully based on remembering your solubility rules, you know that anything that is bound to a 1A metal will be soluble in water, specifically this base, sodium hydroxide. And if it's soluble in water, that means it's going to dissociate. And what does it mean for something to dissociate? It means that it breaks up into its constituent ions. And that's really important for us. So if we add solid sodium hydroxide into water, it's going to dissociate into its constituent ions, which is sodium and hydroxide. Now remember, all 1A metal salts are going to do this in water. We know that all ammonium salts, all nitrate salts are also going to do this, but we were talking about bases. Another thing that's really important, and you didn't maybe realize at the time, but any of the 6 strong acids will always dissociate 100% in water. That means everything that you add into the water is going to break up into its constituent ions. And as a refresher, those 6 strong acids are hydrochloric acid, HCl, hydroiodic acid, HI, hydrobromic acid, HBr, perchloric acid, HClO4, sulfuric acid, H2SO4, and nitric acid, HNO3. So let's do an example. Say that we're adding 1 gram of sodium hydroxide with a molecular weight of 39.99 grams per mole into 100 milliliters of water. Calculate the concentration of hydroxide ions present in the water. So the first thing we need to do is convert 100 grams of sodium hydroxide into moles of sodium hydroxide. We do that using the molecular weight. Another thing you need to understand is that sodium hydroxide, when put in water, is fully soluble and fully dissociates into sodium cations and hydroxide anions. So what does that mean for us mathematically? What that means is that for getting from moles of sodium hydroxide to moles of hydroxide, we can note that there's a simple relationship. For every mole of sodium hydroxide that you have, you will also have a mole of hydroxide ions. Hopefully you see in the chemical formula that for every 1 whole sodium hydroxide molecule or ionic compound, you have only 1 hydroxide anion. So it's a 1-to-1 relationship. Okay, so we know that if we have 0.025 moles of sodium hydroxide, we will have the same number of hydroxide anions that are liberated in the solution when the ionic compound dissociates. So, if we know that we put that many moles of hydroxide anions into 100 milliliters of water, it's pretty straightforward to calculate concentration. Remember that concentration is equal to moles of the thing you're interested in over total volume. Total volume in this case is 100 milliliters, but we can't use milliliters. We have to convert to liters, right? Molarity is equal to moles over liters. That's important. So you do 0.025 divided by 0.1. You find that you have a concentration of hydroxide ions of 0.25 molar. Okay? That's pretty straightforward. That's what we've done a little bit before today, just not with acids and bases. So what does that mean, though? What can we do with these numbers? So hopefully you've all heard of the terms pH, right? Like the pH of whatever is this. And then maybe you've also heard of pOH, which is similar. So to calculate pH, at least, you take the negative log of the concentration of hydronium ions. For pOH, you take the negative log of the concentration of hydroxide anions. Whenever you see a little p in front of something, that little p most often means negative log. And in your calculator, you just hit the negative sign, then you hit the log sign, then you put the number in parentheses. Okay? The relationship between pH and pOH in water is that pH plus pOH will equal 14. So if I give you one of those numbers, you can always tell me the other one, because if you add them together, it should come to 14 if you're in water. There's another thing that we can do is we can go backwards and calculate the concentration of hydroxide anions if we already know the pOH. So hydroxide anion concentration is equal to 10 raised to the negative pOH. And hydronium ion concentration is equal to 10 raised to the negative pH. Now, if you're a little confused about hydronium ions, we'll talk about that in a minute. So, in that example we just did, we found that the concentration of hydroxide anions was 0.25 molar. We calculated pOH, or we can calculate pOH by taking the negative log of that number. Right? This is hydroxide, so it's going to be pOH. pOH is equal to the negative log of the concentration of hydronium ions. Not hydronium ions, sorry, hydroxide anions. So pOH in this example is equal to 0.602, which is totally fine. There are no units for pH and pOH. So now I could ask you, though, knowing that the pOH is 0.602, to calculate the pH. We know that in water, pH plus pOH is equal to 14. We already know the pOH, so you do 14 minus 0.602, you get 13.39. Okay? Let's talk really quickly about this pH scale, right? Probably you've heard about this. So the pH scale in water goes from 1 to 14, and you can have numbers lower than 1, so fractions, and you can also have negative pHs, and you can also have pHs greater than 14. But these numbers correspond to things. So from 7 to 1, that's what we consider acidic. From 7 to 14, that's what we consider basic. The further you move towards 1, the more acidic it becomes. The further you move towards 14, the less acidic it becomes and the more basic it becomes. You'll see that they gave examples of things that have different acidities. Now, what do all these colors show? The colors correspond to what a universal indicator shown down here on litmus paper will turn when exposed to these different pHs. Right? Litmus paper is just, it's really a piece of paper that has chemicals in it that change colors depending on the pH. And so what I've shown here is litmus paper at several different pHs. You'll see that this one, right, is maybe, we'll say pH, we'll say maybe this is like pH of 2, pH of 4. This looks kind of 7-ish, this looks kind of 9-ish, and this is probably like 13, right? Okay? And so that's a universal indicator. It gives you a nice range of colors. There's also red and blue litmus paper, which is just either acidic or basic. It doesn't really tell you how acidic or basic. And you'll see that here, if we start by adding a red and blue litmus paper to a base, the red litmus paper, which represents the acidic side, turns blue, which means that it went from being acidic paper to basic paper, right? The blue paper didn't do anything, which means that it was already pretty basic. For an acid, the red paper didn't do anything, right? It pretty much stayed red. But the blue basic paper turned red. Do you see where it turned red right there? This part? That means that it went from being basic to being acidic. If you put red and blue litmus paper in something neutral, you'll see nothing happens to the paper. And here, when the red paper was put in something basic, it turned blue because it went from being acidic to basic. Okay, and those are just what is the pH scale, why do we have those pH numbers, how can we tell, how can we measure that? right? It has to do with the acidity and the basicity, and we'll definitely come back to this later. So as a final example, let's assume that we add 1.06 grams of nitric acid to 500 milliliters of water. Calculate the concentration of hydronium ions, the concentration of hydroxide anions, the pH, and the pOH. So we know that nitric acid is one of the strong acids, so when we put it in water, it's going to dissociate 100%, which means that it breaks up into its constituent ions. And you'll see in nitric acid that we have H+, which we'll call a proton, and NO3, which will have a -1 charge, which we call the nitrate polyatomic anion. Something that's really important is that when you add protons to water, you should think of them as combining with the water and producing those hydronium cations here, right? We know that hydronium cation looks like this, and the oxygen has a +1 formal charge. Trigonal, pyramidal, molecular geometry. Okay, so anyway, we need to calculate how many moles of nitric acid we added in. That was 0.0168 moles. Then we need to figure out a way to go from moles of nitric acid to moles of hydronium ions. So for every mole of nitric acid, you're going to get 1 mole of hydronium ions. And you're like, well, how did you make that jump, Mr. Hicks? Well, you know that for every proton, H+, that you add to water, you're going to get 1 hydronium ion. And we see here that for every 1 nitric acid molecule, you're going to get 1 proton. So that's for every 1 nitric acid, you get 1 proton. For every 1 proton, you get 1 hydronium ion, which means that there's a 1-to-1 relationship. So you get 1 mole of the hydronium cation, H3O+, for every 1 mole of nitric acid. So it ends up being the same number, 0.0168 moles of hydronium cations. So then to calculate the concentration of hydronium cations, right, we know that we need to do moles over liters. Molarity is moles over liters. So we have 0.0168 moles of hydronium cation over 0.5 liters, which was our total volume, right? We added it to 500 milliliters. We had to convert milliliters to liters, which ends up being 0.5. We find that we have a concentration of 0.0336. So we answered one question. We answered what's the concentration of H3O+. To calculate pH then, we take the negative log of H3O+. So the negative log of 0.0336 is 1.47. So we have a pH of 1.47. I hope you see that that's pretty acidic. That's going to be somewhere in this area here. Okay, so we calculated pH. That's amazing. Now we can very easily calculate pH because we remember that pH plus pOH in water is equal to 14. So we do 14 minus pH, we get 12.5. Then we have to calculate the concentration of hydroxide anions. Remember that the concentration of hydroxide anions is equal to 10 to the negative pOH. We just calculated pOH. So 10 to the negative 12.5 is 3.16 times 10 to the negative 13. That's a really small number, and that's okay. That's totally fine. And the reason why that's fine is because we know that the solution with a pH of 1.47 is quite acidic, which means that we're not going to have a lot of base around. You do have some base around, but a very small amount.